Hello and welcome to this complimentary webinar with the title The Optimal Design, What it is and when to use it. My name is Lennart Eriksson and I work for Sartorius Stadium Data Analytics, and we are a business solution provider inside the field of advanced data analytics. Our solutions are realized through the so-called geometric suite, and the geometric suite comprises 6 different software elements. And what we're going to discuss today takes place in the model software for design of experiments and quality by design. Here we have a little outline of today's presentation. First of all, we will provide a little introduction to the optimal design, what it is and when it is used. In order to bring some clarity into the optimal criterion, we are going to walk through 2 very small algebraic examples just to make the points clear. When you're developing the optimal designs, you often come across 2 evaluation criteria, which are called G-efficiency and condition number, and we will also define these and tell you when to use them. In the middle section of this presentation, we will walk through some typical examples of the optimal designs inside the model software, and the software demo will also demonstrate one of these use cases. At the end of the presentation, there is a little summary and recap of what we have been discussing. So the objective of this presentation is to provide an introduction to D-optimal designs. A D-optimal design is one member in a class of designs generally known as optimal designs. And optimal designs carry this name because they are optimal with respect to some statistical criterion. And this statistical criterion is often connected to the properties of the so-called variance-covariance matrix of the selected model. Alternatively, the variance-covariance matrix can be referred to as the X prime X matrix or simply the information matrix. So there are many versions and twists of this optimal approach, which has led forward to the notion of alphabetic optimality. There are examples called A-optimal, C-optimal, D-optimal, and so on and so forth. And there are between 8 and 10 different optimality criteria that are defined. Now, zooming in on the D-optimal design, the word D refers to the determinant of the information matrix. So a D-optimal design is maximizing the determinant of the information matrix of the selected regression model. What is important to realize is that a D-optimal design is a computer-generated design. It needs an algorithm. You cannot, unlike conventional DOE protocols created by pen and paper, you need a computer and an algorithm. As will also become apparent throughout this presentation, the optimal designs are very flexible and they can be used in many cases where conventional DOE protocols don't apply. And to be a bit more specific, we can say that a D-optimal design consists of the best subset of experiments that are selected from the so-called candidate set. And the candidate set is the pool of theoretically possible and practically conceivable experiments that could be carried out. So the D-optimal approach means that n experimental runs, a subset, will be chosen from the so-called candidate set, such that the n trials maximize the determinant of the variance-covariance matrix or the information matrix. And equivalently, we can then say that the n runs that are selected that maximize the determinant of this X prime X also correspond to the largest volume spanned in the experimental region. So a D-optimal design will select experiments that span the experimental space as well as possible. In this section of the presentation, we're going to zoom in on some use cases where the optimal design would come into play. And the first one we will zoom in on to represent irregular experimental regions. So whenever there is a restriction or a so-called constraint modifying or chopping off a part of the experimental region, a D-optimal design is of interest. To the top, in the top right-hand corner here, we see what would happen if there is a restriction in the situation of a process design DOE. And there are then 2 ways to go forward. Either we try to shrink the ranges of the factors that are investigated in order to get a conventional regular DOE factorial design to be applicable. The price we are then paying is that there will be some regions in the experimental space that are not populated by experiments. Alternatively, we use the optimal design, which is more flexible by sensing the irregularity of the experimental region and still trying to span the space as well as possible. And in the lower part, we represent or illustrate a similar thing, but instead of talking about a screening DOE application, we're looking at an optimization DOE situation. Irregular experimental regions can also arise when you're dealing with mixture designs, when there are bounds on the ingredients in the mixtures that are different from 0 and 1, and one such application is exemplified here. And also here, a optimal design come into play. Another situation when to use the optimal design is when you're dealing with qualitative factors. When you're having multi-level qualitative factors in screening, you can either choose the optimal design or also alternatively what is called the reduced combinatorial design family, the GSD, the general subset design family, available in module 12. So I will not dwell more on that possibility because that is part of a separate webinar presentation. When you're having an optimization design with qualitative factors, the solution will almost always be the optimal design in order to limit the number of experiments. Another situation when the optimal design is used is when you have special requirements. And special requirements or non-standard demands can, for instance, refer to the number of runs. You have experimental material to 14 experiments, for instance, a very fixed desired number of runs that are in between the number of runs encoded by the more conventional DOE protocols. So then the optimal design could be of relevance. It is also of relevance to use the optimal design if you want to upgrade your model by a selected few number of terms in the regression model. For instance, we know that it is the quadratic term of the second factor that would be of interest, but we lack interest or we find the quadratic term of the other two factors x1 and x3 not applicable or not relevant. And similarly, you can also upgrade quadratic models to become partially cubic models by supporting a specific term to your model. Another situation where you would use the optimal design relate to what is known as inclusions. This is a functionality that I think is largely unknown to many users of the model software. Inclusions means that you have been doing a series of experiments and you would like to build on those and complement them as well as possible using new experimental runs. And this can apply both in screening and optimization and is illustrated here. So you have a set of already performed experiments and then you're asking the optimal algorithm to find out a small set of complementary runs that will balance up the ones you have done already in the best possible way. Another situation where you would use the optimal design is when you're simultaneously changing what is called process and mixture factors, when making combined designs involving these types of factors. Process factors in these notations are factors that you can change freely and therefore study and interpret in terms of regular designs such as factorial designs, fractional factorial designs, and central composite designs. And mixture factors are those that you are involved in mixtures where you have an outer constraint constraining all the ingredients in the mixture to sum up to 100%, and where it becomes natural to think in terms of triangles and hypertriangles when interpreting and visualizing the experimental region. If you have attended our trainings, you may have come across an example, a DOE example called loaf volume, which is a typical example where the optimal design could have been utilized. Now, after having overviewed these different situations where the optimal design would come into play, we will now take a little closer look into some theoretical properties of the optimal design. I just remind you what I said in the beginning of this presentation, that you need an algorithm. So a optimal design is a computer generated design, and the design will comprise the best subset of experiments that are selected from the so-called candidate set. So once you're setting up the optimal design, you're going to have to specify which regression model you have in mind. And for that model that you select, the runs that you are picking out of the candidate set will maximize the determinant of the matrix that is referred to as x prime x, or I called it also the variance covariance matrix, or alternatively it can also be referred to as the information matrix. Regardless, the experiments that are making up the experimental design will span the largest possible volume in the experimental region, as long as you have 3 or more factors. In the situations that we will come across very soon, we have only 2 factors, so then they will span the largest possible area in the experimental space. And as I've also said, that the optimal design can be tailored to support a very irregular experimental region, a very complex problem where you would have both process and mixture factors, or where you have a very non-standard demand on either the model or the number of experimental runs that you want the experimental design to contain. So we will now try to get more familiar with the optimality approach, and we will do that in terms of 2 small examples. The first example is a case where we have 2 factors, which we call x1 and x2, and we have performed a 2 raised to the power of 2 full factorial design. And we see here the experiments that have been performed. We have the usual pattern minus, plus, minus, plus, minus, minus, plus, plus. And with these 4 experiments, we have the possibility to calculate the regression model with as many terms as we have experiments. So if we have 4 experiments, the model can have 4 terms. We have the constant term, we have the linear effect of the first factor, we have the main effect of the second factor, and we have the 2-factor interaction. And in the data analysis, it is the numerical values of these so-called regression coefficients we would like to calculate. And that is done by using least squares analysis, and the calculations can be expressed in matrix form, and when we solve that, the regression coefficients are given by this expression. And when we see x here, that refers to part of what we're seeing here in the experimental matrix. The X matrix has actually 4 columns. It will have 1 column for the constant term. It has the second column here for the encoding the main effect of the X1 factor, and it has another column for encoding the main effect of the second factor, and the X matrix will also have a 4th column encoding the 2-factor interaction, which we can see here. So here we have the X matrix in its full extent, and when we are calculating the regression coefficients, we're going to work with the transpose of that matrix and also finally invert the X prime X matrix, and these steps are illustrated on the next slide. So here we have the original X matrix, 4 columns, because the regression model had 4 terms. When we're transposing X to become X prime X, what we're doing is that rows become columns and vice versa. And then we are multiplying X prime by X, and then we obtain a symmetrical diagonal matrix, which has the value 4 on the diagonal because we have 4 experiments. And in the calculation of the regression coefficients, we're going to invert this X prime X to become this. And it is the properties of this inverse of the variance covariance matrix that is closely connected to the precision in the regression coefficients. The precision is usually expressed in terms of a 95% confidence interval or some alternative selected level of confidence. The precision is given from the properties of this inverse of the variance covariance matrix times the residual standard deviation of the regression model times the t-value coming from a t-distribution reflecting the degrees of freedom and the selected level of confidence. So from this it follows that the smallest regression coefficients comes either from the smallest inverted X prime X or the largest X prime X matrix. And if you're maximizing the determinant of the X prime X, it means that you have a optimal design, and that will then be going going back to very small contribution to the uncertainty of the regression coefficients. So if you have a large determinant of the x prime x, that corresponds to a small addition in the confidence interval around the regression coefficients of the selected model. So let's see how this works. So now we have taken a step further. Instead of having just two levels of the factors as we had in the first small d-optimal example, we now have three levels in the two factors in the second d-optimal example. The proposed model is just a linear model now. We have skipped the two-factor interaction, so it means we have three terms. We have the constant term, we have the main effect of the first factor, and the main effect of the second factor. So this model needs 3 degrees of freedom, or 3 experiments. We can see here the candidate set. The candidate set has 9 experiments, and it is from this candidate set we wish to extract 3 experiments making up our d-optimal design. Now, when selecting 3 trials out of 9, that can be done in 84 different ways from this expression. So the question is, how would we select 3 trials out of 9, given that we have 84 possibilities of doing that subset selection? Well, the answer is, of course, we would like to maximize the determinant of x prime x, because that would correspond to having the narrowest confidence intervals of the regression coefficients of the model. Now, in order to illustrate the connection between an increasing determinant and the larger and larger area covered by the subset selected, we're going to walk through a couple of plots. So if we would select this subset of 3 runs out of 9, you could see that they will define a line, but they would not span any area, and the determinant for this subset selection is 0. An alternative subset selection would be this 3 experiments out of 9, and they cover a slightly larger area, and they have a determinant of 1. We can see that when we go up to the determinant of 4, we cover a larger area still. The determinant of 9 and 16 gradually corresponds to increasing area covered by the 3 experiments that are selected out of the 9 possible. So in this case, the best precision in the estimated regression coefficients would be encoded by the subset selection with the determinant 16. Now, on the next slide, we will then be looking at how to calculate the determinant for a given 3-run subset selection, and we will illustrate that using this selection corresponding to a determinant of 4. So here we have again repeated the distribution of the experiments that spread according to a determinant of 4. We can see that the coordinates for these experiments are -1, 0, 0, -1, and 0, 1. These are the coordinates of these 3 experiments. And so we have the X matrix of the selected model, we have the X prime, and we have the X prime X. And it is this matrix that we are going to calculate the determinant for. And calculating the determinant means that you're forming product of diagonal elements, and then from that product you are subtracting the product of the diagonal elements for the diagonals running, so to say, in the opposite direction. And the full calculations are given in the lower part of this slide, and that eventually becomes 4. So with these 2 small algebraic d-optimal examples in mind, we can now summarize some of the features that comes with the d-optimal approach. One thing that we have always to remember is that the d-optimal approach assumes that the regression model that we select is correct and true. So there is a sensitivity to model choice, and in an unlucky situation, if you start out with selecting the wrong model, it can be so that the experiments that you have done do not fully support a more complicated model if needed. However, we can add something called potential terms as a safeguard to protect against this sensitivity of model choice. When we are developing the optimal design, the model software solution provides a number of evaluation criteria. We would like to lift out 2 of those and zoom in on those because they are the most common. The first evaluation criterion is the so-called condition number, and if you have been attending any DOE training that we are providing, this statistic is probably familiar to you. The condition number represents the largest of the ratio of the largest to the smallest singular value of the X matrix. You can say loosely that it is a measure of sphericity, or how balanced a distribution you have of experimental runs in the experimental space. And the lower optimal value of the condition number is 1.0, which denotes a perfectly orthogonal design. The problem with the condition number is that it doesn't really indicate how many experiments is contained in the DOE. It will just compute a statistical measure. It is not reflecting the work labor, you can say. Alternatively, we also use the G efficiency, and the G efficiency is computed using the following expression, where P is the number of model terms, N is the number of runs in the design, and D is the maximum relative prediction variance, prediction error across the candidate set. Now, the interesting thing with this statistic is that it is, you can say, weighted depending on the number of runs contained in the different d-optimal designs. So the G efficiency will compare the efficiency of a d-optimal design to that of a nearest fractional factorial design. So 100% is the upper limit, and it designates actually that we have obtained back the fractional factorial design or full factorial design if they are available. And we should also remember that designs like fractional factorials and full factorials are also d-optimal. They, so to say, represent the limiting case of d-optimality. Experience-based, our recommendation is that if you get the d-optimal design with a G efficiency of 60 to 70%, you have obtained a very good and useful d-optimal design. This brings us over to the next section in the presentation, where we're going to very quickly walk through some typical examples in the model software solution where the optimal design has been successfully used. First of all, we have the situation of irregular experimental regions, and this can be studied and evaluated using something called the constraints functionality in the model software. We have here a little example, which is the one I will also be demonstrating later in the software demo, where we have two factors. We have the reaction temperature between 400 and 600 centigrades, and we have a pressure between 1 to 3 atmospheres. And in this particular application, you cannot perform experiments at the same time when you're having high temperature and high pressure. So there is a little part of the experimental space that is inaccessible because of this unlucky combination. Now, there are two ways to impose constraints using the constraints functionality in the model software. Either if you know by beforehand the equation of this inequality, you can type it in directly in this constraints field, or you can try to define the constraints using a graphical help functionality by clicking and dragging on these small handles, trying to position the line, chopping off, in this case, the top right corner where you think it is appropriate. You can also modify the positions of the handles by typing in the coordinates in the coordinates field here, and also decide whether to exclude the experiments above the line or below the line. And in the right-hand part of this slide, we see the resulting d-optimal design supporting an optimization objective, a quadratic regression model. Another very common application of the optimal design, showing some illustrations from the model software, is what is called model updating. And this is very common after screening when it is necessary to unconfound two-factor interactions that are mixed up. The application that we're showing here is our tutorial example called laser welding. Without going into too much details, we can say that for one of the responses, which is the width of the weld, after running the analysis wizard in the model software, we have arrived at the situation where we have the four linear terms and the two-factor interaction between the two first factors. Now, the problem is that the two-factor interaction between the two first factors is also going to be mixed up or confounded with an alternative two-factor interaction occurring between the third and fourth factor. Now, there are different ways to try to add more experiments to the initial experimental design in order to resolve the confounded two-factor interactions. The classical way of adding more experiments would be the so-called fold-over approach, which is rather resource intensive and would lead to 11 new experiments. You would be guided and recommended to do as many new experiments as you have already performed. Alternatively, you can do a selective updating with the optimal design, where you're specifying that it is particularly this two-factor interaction that you are targeting. And here we see the resulting design that is tailor-made to resolve two of the mixed up two-factor interactions. And in this case, only 6 experiments have been added to complement the initial 11-run fractional factorial design. The last example we're going to walk through or illustrate is when you have a combined design situation involving both process factors and mixture factors. And again, we are relying on one of our tutorial examples, in this case, the bubble formation example. So it's about blowing bubbles with the children's bubble wand and trying to make the lifetime of the resulting bubbles as long or as high as possible. In this example, there are 2 so-called process factors. It is the temperature where the bubble formation is blended and the mixture settling time. And then there are 4 mixture factors. There are 2 dishwashing liquids or washing up liquids, water and glycerol in the mixture formulation, you can say. In addition, there is also some relational constraints constraining the sum of the dishwashing liquids to always be between 20 and 50% of the total mixture solution. In this case, in the first part of the bubble formation example, we run a screening where the selected model was one with the linear and interaction terms, interaction between the 2 process factors, interactions between the process and mixture factors, but no interactions between the mixture factors themselves. Now, before generating the optimal design, model will conduct a little overview of how many experiments would be needed to support the selected model. In this case, the selected model needs at least 20 experiments. It has around 15 degrees of freedom, and always adding 5 degrees of freedom would lead to a total lead number of experiments of around 20 experiments to start out with. So what will happen is then that when we are generating the optimal design, we will start from this lead number of design runs, which in this case is 20, and then generate alternative designs with modified n of around plus minus 4 around the starting lead number of n, and then make between 5 and 10 alternative versions for each level of n in plus minus 4 runs. So in this case, we are going to investigate the optimal designs running between 16 and 24 experiments and calculate 5 alternatives for each level of n. That means 9 levels times 5, so 45 alternative the optimal designs were calculated, and the G efficiency of these 45 designs are shown in this plot. And we can see that one of the designs with 16 runs had the highest G efficiency of 76.1% and a condition number of 2.7, which is a really good design. And this is the design that was selected to perform the bubble formation experiments. To this set of 16 experiments, a couple of replicates were added, so the final design had 24 experiments. And we see the screening design on this slide. We can see that the shortest lifetime of the resulting bubbles is 11 seconds. They are bursting very rapidly, whereas the longest lifetime produced was slightly over 6 minutes, which is a considerable change in the lifetime span. So these results were evaluated, the model was proposed, and the model software optimizer was used to propose even more prosperous conditions. And after running also an optimization design, we are not showing the results of that stage, it was actually possible to increase the lifetime of the bubbles from slightly over 6 minutes to more than 22 minutes lifetime. And the key to prolonging the bubble lifetime was to increase the amount or the proportion of glycerol quite substantially. So after having gone through these applications, we will now go over to the model software and provide a software demo. And after the demo, we will again come back to the PowerPoint part for a couple of rounding off remarks. So we're going to create a new experimental plan if just MODE will start. And if you if you're not familiar with MODE, I will towards the end of this presentation point you to a recorded webinar where you can see the basic function of the MODE software. Here we're just jumping into what we call the design wizard. We will define the temperature, which is the first factor, and it's measured in degrees centigrades. The low setting was 400 and the high setting was 600, like that. And then the second factor was pressure in atmospheres. The low setting was 1 atmosphere and the high setting was 3 atmospheres. And then here we have a little tool where I'm now pointing that in many cases the user aren't using because they're working with regular experimental designs. Place constraints on the experimental region. Now what happens when you click next in this dialog is that you have a chance to type in the inequality chopping off the, so to say, the top right hand corner. If you don't know that inequality by heart or by experience, you can click finish and exit the design wizard, and then under the design tab open up this graphical help by selecting the constraints tool. That will open up this little dialog that you saw on one of the slides in the PowerPoint part, where the initial field also has been augmented with this graphical possibility. So we first have to select, well, we just have 2 factors, but potentially you can have more factors. Then you can either type in the coordinates in these fields directly from the keyboard, or you can pull these handles by clicking and dragging and releasing so that you're defining where you think that the inequality will be. And then you have the exclude area to set, you have to set it to exclude above the line. So the red part will now be excluded from experimental points, and you can then modify so either these coordinates or the, so to say, size of the corner you're chopping off looks good. And then you click add, and then of course you can add other constraints, taking away the lower left hand corner and so on. You can mutilate the experimental space quite freely by this approach. So we now click save and close, and now when we go back to the design wizard, we can have the possibility to click in a response, but it's not really critical in this little demonstration. Like that. Then when we select what we have, what objective we have, the only choice will be a de-optimal design or perhaps an onion de-optimal design. And now the lead number of design runs has been calculated silently in the background by the MODE software by looking into the selected model, which is a quadratic model in this case. We have some extra degrees of freedom that we have to use because of these constraints, and it then proposes 12 as the lead run. In these 12, always the calculated center of gravity will be included. So if you just want 3 replicates, you can lower the number of center points to 2 because one of those 3 will be part of the lead number of n. And then we can have a design run span, let's say plus minus 3, and we can do 10 alternatives. You can do up to 200 different de-optimal designs when you're launching the de-optimal algorithm. So in this case, we're generating a total of 70 designs. We click next, and then we are by default auto-selecting the best design using this G-efficiency criterion. So we will have to browse through this list, and it has highlighted a design which has 78.35 in G efficiency, and in fact all the different combinations or alternatives with 9 runs seem to have the same G efficiency and condition number and so on and so forth. So it means it's a very stable situation. We can also display this as a plot if we want to, and then when we click finish, the worksheet for the selected design will be created, and you have then 3
identical points in the bottom. Two replicates from the setting 2, and the third one from knowing that that point will always be part of the optimal choice. We can use the scatter plot tool here to visualize the distribution of the different experimental points, and you can see here how it has recognized the constraint chopping off the top right-hand corner. And what is happening when we cannot do experiments in the top right part can also be summarized through the correlation matrix. We can see that the terms in the regression model are partly correlated, and that is the price we pay if we cannot lay out experiments in a perfectly symmetrical fashion. So what happens is that we start to get small non-zero values in the off-diagonal elements in the correlation matrix, and the final effect that we'll have is that we will have slightly widening or slightly increasing sizes of the confidence intervals surrounding the regression coefficients in the resulting model.
So we are now, after having gone through the demonstration of the model software for the optimal design and the constraints functionality, we are now back in PowerPoint, and I'm just going to provide a couple of rounding off remarks. So what we have discussed in this presentation is when to use the optimal design, and basically that is when you have irregular experimental regions or very non-standard or odd demands on the model or the number of runs, for instance. We have discussed the optimal design, what it is. We have gone through computational and geometrical aspects of the optimality criterion. We have highlighted that one useful evaluation criterion is the condition number, but an equally important and useful alternative measure is the so-called G-efficiency, because it will also pay attention to how many experiments are contained in the different versions or different proposals for the optimal design. The applications that we have discussed involves constraints, and that this is that's the use case I demonstrated. Model updating, multi-level qualitative factors, and combined designs of process and mixture factors. And with these words, I would like to thank you all for your time and attention. I hope you find this presentation useful. Thank you very much.